Good day, everybody. Today we're going to look at a plethora of averages, mainly on the half circle and the hemisphere, but also on the inside, and just trying to understand averages and line integrals, double integrals, triple integrals a little better. So let's see. First, I'll look at the upper semicircle and find the average y value. So one of the things you learn early in calculus is the average value of a function is 1 over b minus a times the integral of the function, which is a line integral. It's just the integral divided by the integral of 1. So let's see. So for my function, square root of 1 minus x squared, unit circle, top half, that integral is pi over 4. If you take the integral and divide by the length of the interval. As a line integral, I'll get the same thing. I integrate sine squared divided by sine. So how does that come up? I'm going to parameterize, so I go left to right. So to start on negative 1, 0, then do the upper circle and end up at positive 1, 0. This will be my parameterization. So here is ds, it's just 1 dt. And so the integral of y dx is y. And dx will be sine as well, so I get sine squared. And then that integral will be pi over 2. So I got pi over 2, and then the length of the interval is 2, which you would get by integrating just dx. You'll get that 2 there that way. So either way, we're going to get pi over 4. Pictorially, there's a couple ways to visualize what's going on. Essentially, it's like we're taking points equally spaced along the x-axis, send them to the curve, and then average their y values. If I do that with 20 points, it's 10 in each quadrant, then this will be the average of those 20 points. It's already pretty close to pi over 4. And if I say double the number of points, oops, let's see if we can do it visually or not. There we go. So 20 points. And I got a little closer to pi over 4. Maybe I'll double one more time visually. There we go. So there's 80 points equally spaced along the x-axis, 40 in each quadrant. And I just keep getting closer to pi over 4, the higher the number of points. Like if you go to 1,000, get even closer. Another way to visualize the average is that pi over 4, if you go back to the definition, the average value times b minus a gives you the area under the curve. So you're essentially looking for the y value that the area would collapse to, which would be this. So if this were somehow water level and then it could go flat, that's the level it would go. Or this area above the line wouldn't be able to fill in the area below the line, because they both have the same area. They both have area pi over 2. Another way to find the average value of a curve is with respect to its arc length. So to do that, you integrate the function ds and then divide by the length of the curve. So here I have to do it parametrically. So this is the integral of y ds divided by the length of the curve, and that'll be 2 over pi. One more time looking at this. So if you parameterize a circle, the top half of a circle, it doesn't matter if you go left to right or right to left when you do the ds integral, but either way, for the unit circle, ds will just be 1 dt, and so y ds will be sine dt, and we'll integrate from 0 to pi. And then you divide by the length of the top half of a circle, which is pi, 2 pi being the full circle. So there's our average value, and that's different than pi over 4, which was like 0.78. So pi over 4, about 0.7854 almost. one way to visualize this. So here's the curve, and above the curve, I plot what's the y value, and so we want that integral. So in a way, it's kind of that area. So another way to visualize what's going on is that we'll take points equally spaced, but not along the x-axis, and then send them to the curve, but equally spaced along the curve itself. So here's 20 points, and then what's the average y value of those 20 points? 0.637, and it's already pretty close to 2 over pi. And if I do more points, as I go to 40. So there's 40 points equally spaced along the curve. Find that average y value of those 40 points, and we're going to converge to 2 over pi. So that's a different result. Again, more points means get closer to the true average. If I compare the two averages, so here's a plot of when there's 20 points equally spaced along the curve and with respect to the x-axis, and you can see they get higher faster because of the steepness. You go higher faster, so it's kind of a density thing, and no matter how many points you have, you think well, as you went to 1,000,000 points, it won't matter. But again, they're going to be concentrated higher if it's equally spaced with the x-axis, more so than equally spaced on the curve, no matter how many points you have. Now, instead of just that boundary, the curve, the half circle, I'm going to look at kind of the half disk. And so now I need, for the average value, it's the double integral of the function divided by the area of the region we're doing our double integral. And I want to find the average y value. So my function is just going to be y. And then on the half disk, that area is pi over 2, half a unit circle. So here's the integral. In two forms, you could do it, integrate from 0 to the top of the circle as x goes -1 to 1. Integrate y, and then divide by pi over 2, or do it in polar. Integrate y, which is r sine theta, times r dr d theta. So that would give me this integral divided by pi over 2. Either way, so the limit's 4 over 3 pi. One way to visualize this would be above each point in that disk, what's the y value? So here's a graph of y over that half disk, and then I'm finding the average value of this function. It's 4 over 3 pi, about 0.42. Or for average value, let's look what I got here. I want to find points equally spaced on the inside of the circle. So here it is with 200 points. I've got 20 rows or 10 rows and 20 columns, I should say, of points. Find the midpoint, and some of them are inside the circle and some of them are not. I was able to count them just by using sign, whether you're inside or not. And so at first there's 200 points in the rectangle. 158 ended up being inside the semicircle. So the ratio is 0.79, which should be the ratio of the areas. Pi over 2 divided by 2. The area of this rectangle is 2 by 1. This is half a unit circle, so this is area pi over 2. So pi over 2 divided by 2 is pi over 4. So that's what it'll approach. That's just the area. And then if I average those y values, it's already pretty close to 4 over 3 pi. Let me bump it up a few here. Just go slowly. 20. So there, if I double, I don't think anything changed with the pi. So change this to 20. So it's still 0.79. I don't know why it well, it wasn't uniform. I mean, in general, it does go to pi over 4. But here's the average. I don't remember if that changed. If I go to 40. All right. So now, what fraction of the circles? Yeah, now it's a little closer to pi over 4. Right? That's about 0.7854. So I got a little closer finally. And the average of those y values, again, gets closer to 4 over 3 pi. One more doubling. I'm sure we have the picture by now. So there's 80 rows, 160 columns. And again, so now we're definitely getting closer to pi over 4 of the percent that are in the circle. And the average of those y values of those that are in the circle is getting closer to 4 over 3 pi, as expected. Next, I want to find the average value of the z values on the hemisphere. Okay, so here's a hemisphere. So we're going to be on the hemisphere. There's a couple ways to do that, just like with the half circle. We can do it with points equally spaced in this disk brought up to the hemisphere. And that would be like this. So we've got, here I've got a 20 by 20 points. And if I project them to the hemisphere, let's see, so here's another way, R3. Here's the 20 points. I'll project them up to the hemisphere. I kept it solid this time, but so here they are. So 400 points, although not all are inside the circle, but projected up to the hemisphere. And then I can average those z values. So if I do that, first the percent of points in the circle is again going to converge to pi over 4. So 4 times that ratio converges to pi, the circle. Right, so we've got a 2 by 2 and a pi area. So pi over 4 is the ratio, and 4 times that should go to pi, which it will. But when I find the z values, it should converge to 2/3. And right now I'm at 0.66. So let's bump it up a little. Say 40. Double it. So there we got more points equally spaced in the domain, projected up to the surface, average those z values, and well, didn't get too much closer. I'll double one more time. I think this is the limit of the pictures here, so it was actually 80 by 80 in each quadrant, so I think it's 160 by 160 is the number of points. So quite a number of points. Let's average the z values. So now we are getting closer to pi over 4 or pi for the area of the circle we can see. And the average z value is getting closer to 2/3. Pictorially, the average is the height if you squished everything. Back to this definition, the average value times the area of the region will give you the area under the, or the volume I should say, under the surface. So 2/3 is what the height would be if you squished a hemisphere flat. Right? The base is pi, and 2/3 pi is the area of a hemisphere. 4/3 pi, area of the full, the volume of the full sphere. Keep saying area, volume. Anyways, so that would be the average value. But that was points equally spaced inside kind of its domain. If you take points equally spaced on the surface, then I need a surface integral. Whoops. Well, all right, so here's the, I haven't done the double integral yet. I thought I did it. Average z value on the, all right, so, well, if I haven't done it, there it is. So 2/3, I guess I stated it, and then there's the work. So a couple ways to do it. You can either do it in rectangular or polar coordinates. So the z value or I should say the function square root of 1 minus x squared minus y squared. So in polar, it'll be that. All right, so 2/3. Again, the average is above 1/2 because it's steep, so you kind of go up fast. You don't see it as much, I guess, when there's this many points, but you go up fast. So it seems like there's more points higher than lower. So the average ended up being above 1/2, perhaps surprisingly. If I take points equally spaced on the surface, now it will converge to 1/2. It's not so easy to plot points equally spaced on the surface. I kind of did my best here, but you just have to mentally picture it for the most part. It got really hard at the top there. Points equally spaced. Let me try. Not too bad for the lower values, but just picture points equally spaced on the surface itself. It's kind of the same difference as equally spaced on the curve itself versus equally spaced in its domain, then brought up to the curve. Anyway, and well, the more points I have, so that's with 80, but that's not 80 points obviously, but it's complicated. How it was done, not worth going into. You can kind of see, I guess it's 80 squared points. But the average does converge to 1/2. It's kind of complicated how I got the z value. I kind of overthought it. Maybe just a quick look, which I won't go into. But if you take a half circle, and instead of doing the middle, I did the middle where the arc length was. So if you solve for the arc length between x1 and x2, like say from 0.4 to 0.5, if you find that arc length, and then where would the middle arc length be? It ended up being the sine of the average of the arc sines at that endpoint. It didn't make too much difference, to be honest, but that's what I use for the z value. So where the arc length would be the middle. So not quite the middle z's, and I went up, but don't worry about how the sausage got made there. So here would be the surface integral. We integrate over the surface f, but f is just going to be the hemisphere, square root of 1 minus x squared minus z squared. So different ways to do that. I can do it in spherical coordinates with row 1, and you get 1/2. Or I did it in rectangular, and I still got 1/2. So the average z value that way on the points on the surface is 1/2. Okay, so equally spaced on the surface, average z ended up being 1/2. Equally spaced in that domain, then brought up to the surface, average z value is 2/3. The last average z value I'll do is on the solid hemisphere, the solid hemisphere. So I'm going to take points equally spaced in this 2 by 2 by 1 rectangular box. Some will be inside the hemisphere and some won't. The ratio of the volumes, so 2/3 pi divided by 4 is pi over 6, is the ratio of the points that ended up inside the hemisphere. And it's already pretty close. And 3/8 is what the average z value is going to be of those points that were inside the hemisphere. So I'm already pretty close. Let me bump it up. So I think this is 20 by 20 by 10. I think in each octant there of those. here's the ones that ended up inside the hemisphere. So I'm thinking of the solid hemisphere, not just the surface. I don't know how much more I can handle pictorially. All right, so quite a large number of points there. I think I hit my limit for the graph, but we can still do the sum. So it's starting to look solid. So the fraction of those points that were inside the hemisphere, it's converging to pi over 6, 2 pi over 3 divided by 4. Volume of the hemisphere divided by volume of the rectangular box. And 3/8 is going to be the average z value of those points. And it's getting closer and closer. And as n gets bigger, it'll converge more to that. That would be a triple integral average. So you integrate f divided by the volume of the region. So I did that 3 ways. 3/8. That was rectangular. Here we are in cylindrical and spherical. So integrate z dv. So z dv for the hemisphere. And then divide by the volume, 2/3 pi. Z dv in cylindrical and z dv in spherical. So that's a way to visualize some of these different integrals we have. Hope you enjoyed that. Thank you, and have a good rest of your day.